4:30. Okay, why don't we get started? So today we will pick back up where we left off last time and finish out the module on the information pertaining to regression. And so when we last left off, we talked about this hyperplane and we gave two examples of the squared error loss. And so what we're looking at to refresh your memory from last Tuesday, the so-called regression model. And in a regression model, it is still a linear model, just like in the classification case. Only the difference is the hypothesis h of x outputs a real valued number. And so as such, we have our label instance pairs, our xi, yi, where for each corresponding input feature vector xi, we have some real value yi, right? So pertaining to the credit example, instead of a yes/no answer, +1, -1 answer as to whether or not someone should be extended credit, for that same application domain, you can imagine the output of this linear model, the regression model, is the amount of credit someone should be extended. So when we last left off, we talked about our hypothesis G, and we gave two examples in the frame on the left, your left. We have a single dimensional 1D regression model. Now, of course, you can see the graph is two dimensions, but in this case, the horizontal dimension is your input feature. It's one dimensional, and the vertical axis in this depiction is your regression output, your real valued label associated with the input. In the second frame, the frame on the right, your right, we have a two-dimensional input representation. So we have x1, which might be something like the number of years in residence, and we have the x2 feature, which might be the annual salary. And in this case, the x1 and x2, those are components of a single x vector. And so if you were going to write this out in a little bit more elegant notation, right, you do something like the following. So you'd say I have, and that marker's dry. Let me put this away. Let's see if I can find another marker. There we go. To make the notation a little bit more elegant, you might do something like the following. You have vector notation, and you say I, representing the ith feature vector. And then if you were to describe this, you'd say xi1, xi2, where the xi1 and xi2 represent the first and second feature of the ith feature vector, right? So then if you're going to draw this as a 2D regression model, you'd say this is the xi, let's see, is that 2? xi2 axis, and this is the xi1 axis, right? And those are unit vectors. And then, of course, here we have our y-axis, but that's just notation. Now, certainly in the book and in many descriptions of what these things are, they try to simplify things as much as possible, but it can be a little bit confusing when you see x1 and x2 labeling the feature axes in this 2D model, and then we've been saying x1 or xi representing the feature vector itself, right? So just to kind of think about if we were to tighten up the notation a little bit to be a little bit more descriptive of what's going on. So a single vector xi, right, in that notation would represent one of these points. And if you think of each point here in this two-dimensional regression model, it has a projection along the first feature axis, and it has a projection along the second feature axis. And so that projection here, if we were to return back to this diagram, if this is a particular point, we draw its projection on the x1, x2 plane, and its projection along this axis would be xi2, and the projection along that axis would be xi1, right? Where this vector would be the ith vector in two dimensions. Does that make sense? Okay, so then certainly if we were to take this point and we project it along the y-axis, this is going to be yi, which is the real valued label associated with xi, and so that xi is associated with a value yi such that yi like all the y's are from the real set of real numbers. Okay? All right. Any questions about this? Okay. So here we have a measure of the coincidence between our working hypothesis h of x and our ground truth target function f of x. And so we use the squared error loss because we want to know that difference, but we're not concerned about whether or not that difference is positive or negative. And so certainly if it's positive, it's uh, below the, if it's positive, it's below the plane, this point. If it's negative, it's above the plane, right? Uh, but nonetheless, we square it because we're not concerned about the difference. We're not concerned about the sign, I should say. We're concerned about the magnitude. And so this is for a single x vector, right? xi. And if we want our error as it pertains to our data set, we need to now incorporate all of these individual so-called point errors across all the data sets, all the examples that comprise our in-sample data. And so across in-sample, we compute the average, right? So in-sample error associated with a working hypothesis h of x is just going to be 1 upon n, and then we take the sum of all the squared error losses across each of those n many points. So we get the sum for little n goes from 1 to big N being the number of label instance pairs we have, and we take the squared error loss between h of x and our ground truth f of x, which is y sub n, and then we take that average, 1 upon n, for that summation. Any questions? And so if you can think about it, what we're essentially doing, if h of x is governed by some weight vector w, we're essentially choosing a different value w, i.e. choosing a different line, so that we minimize the average distance between those points, ground truth, and the plane, right? And so in one dimension, we have a line on the plane. For a two-dimensional regression model, we have a hyperplane in 3 space, and that carries on if we had 3 feature vectors or 4 or more. Okay? All right. Any questions about this? Does that make sense? Yeah. So that's where we left off. Okay. So let's carry forward and we'll take a look at this expression and we'll develop a solution for it in coming up with our final best hypothesis. So we have this expression for in-sample error. So what we're doing here is we're taking our definitions and we're replacing them, putting them in vector matrix form, and then working forward from that. So on this top line here, we have our expression for in-sample error, our W transpose X, and that should be a little n here. That's a typo. I apologize for that. Sometimes you don't see these things until it's really big on a board, right? So we have our h of x, which is W transpose x sub n, and we have our f of x, which is our ground truth real valued label associated with our x value, and that's just going to be y sub n. And we have that expression for in-sample error, right? So now we're just substituting for what f of x is and what h of x is. So now we're going to make a replacement here. We notice here that every time we have a W, we take the inner product between W and each of the input feature vectors. And so if we take x1 and x2 and x3 and x4, we're applying that for all of the big N many input points that comprises our data set, our in-sample points. And so in vector matrix form, we have the following expression. And before I continue with that following expression, let me first explain the components of that expression before we talk about the expression itself. So we're going to define capital X, and capital X in statistics is called a design matrix. And we make the assumption that all vectors X in d plus 1 dimensions, because remember, when we're talking about the model, we have this augmented X vector, which was the original features, but we've also included an additional feature, this X naught, which was fixed to 1, right? Likewise, we have this W, and remember we had W1 through WD for d-dimensional feature space representation, but we took this minus T, our threshold, when we're first developing the classifier model, and we absorbed that into a dummy variable called W0, W0, right? And so we took our W0 and our W and our X rather are in D plus 1 dimensions for that reason. D of those dimensions are the original weights and the original features, and then that additional 1, d plus 1. That For the w's, it's that w naught that makes it d plus 1, and it's the x naught that makes it d plus 1 dimension for the x's. So now we're going to make the assumption that each one of our vectors is, by definition, a column vector. So that means if we have x, a typical x sub I is going to have um, an x naught, or more correctly, I should say an xi0, an xi1, dot, 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 up to and including xid, right? So we have d plus 1 as our rank for this particular vector as the dimensionality. So if our vectors x are column vectors, right? If you take the transpose of a column vector, you have a so-called row vector. It's nothing more. If we say xi transpose, that's just a 1 by d plus 1 vector or matrix or system. So here, the dimensions of this, it's d plus 1 rows by 1 column. Here, we have d 1 row by d plus 1 columns. Okay? So if our vectors are natively column vectors and we take the transpose, that turns our column vector x, which is of rank d plus 1, turns it into a row vector. And now as a row vector, we can take all of those big N many row vectors, all right? And you notice here in this notation, I said x1 vector transpose, x2 vector transpose, right? And we can construct a matrix we'll call big X, and this big X is such that each one of the rows of this big X represents one of those data points, one of those vectors, okay? And so for that reason, because we have n many data points, that means we have n many rows. So the row rank is going to be big N, and the column rank is going to be d plus 1. So we have a linear system here, big X, that is n by d plus 1. Does that make sense? Any questions? No? All right, so this has a term in statistics. This big X is often called a design matrix. And a design matrix is just there to put all your data, and it allows you to apply linear transformations from linear algebra and to make manipulations en masse on your entire data set, right? That's what its purpose with. So what do we do here? So if we were going to look at this W transpose X here for our in-sample error, what we're doing is we're taking every single x vector, for x goes from the first one up through big N, and we're multiplying that by w. One way we can achieve that is to take each row of the design matrix and multiply that by a w vector, right? So w is a column vector. So you can imagine if we were going to write this w column vector right here, well, how do you do matrix multiplication? Matrix times a vector. You take the first row and you multiply it by that column. You take the second row, multiply that by the column, and so forth. And so one way of incorporating this W transpose X for each one of these X vectors, right, representing the data points, is to construct your design matrix and multiply that design matrix by your column vector W. And again, W is of rank D plus 1 because W includes all of the original weights, W1 through WD, as well as that W naught. Does that make sense? Any questions? Yes. N by D plus 1. Yes. Y is going to be N by 1. Right? So I haven't gotten to Y yet, and I'll get to that right now. All right. So we have our big X matrix, our design matrix, right? So big X consists of X1 transpose, and it's a so-called row matrix, right? Each of the individual vectors is placed as a row major in this design matrix, right? And so each one of these is d plus 1 dimensions. So the rank of x is going to be n rows by d plus 1 columns. So now we have our w vector. W, right? We said before, W is a column vector because we are assumption or our convention is that all vectors are column vectors, which is why you write transpose here. And W started out as the original weights, W1 through WD, and we augmented this with W naught. So W is going to look like the following. So W is going to have W1, I'm sorry, W naught, W1 up to and including W sub D. So that means we're going to have D plus 1 rows by 1 column for our W. Okay, so now we have our Y vector. Now remember, when we had our original data, we said our data was a vector x1, x2, dot, 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 up to and including the nth in-sample point. And associated with each x vector was a y value, where each y value was drawn from the set of real numbers. So corresponding to x1, we have y1. Corresponding to x2, we have y2. And so forth, corresponding to xn is yn. And so if we were going to note this a little bit more compactly, we have a bunch of so-called label instance pairs. So if we were going to generally talk about a single data point and its ground truth real value class label, we'd say xi and its corresponding yi. Okay, for I goes from 1 to n, where big N is the number of data points. So if we were going to represent all of our y values as a vector, as a column vector, well, we could represent that as a big vector y, and y is just going to be the vector that has all of these real values associated with each of the x's. So corresponding to the first x, you're going to have y1. Corresponding to the second x, you're going to have y2. Likewise, corresponding to the nth x vector, you're going to have y sub big N, right? And so for this reason, you're going to have n rows, big N, by 1 column, okay? And so to answer your question, this y vector is going to be a big N by 1 as its rank, and it's a column vector, okay? All right, so if you imagine having a W, and I really wish the slide, I take pictures from the book just because so that you read along in the book, and this kind of mirrors what's in the book. But you can imagine if I had um, uh, a a d plus 1 by n vector here, right? W as a column vector. Well, I take this row, that's d plus 1 positions, and I multiply that by that W vector. That's exactly my W transpose X, right? Now, certainly in the original expression of in-sample error, it's written a little bit differently, but mathematically, it's the same expression. It's all of the positions of the X vector multiplied by each of the positions of the W vector for each one of those positions, the 0th through the dth position. Okay. Questions? Does that make sense? So we have that part. We can get this W transpose X behavior by multiplying the design matrix by our D plus 1 vector W. And then after that, we can get the rest of this expression, the comparison to the ground truth class label, by just subtracting off that Y vector that we've constructed of all the Y values associated with each one of the input X vectors, right? So if we make that computation, that takes care of what happens inside this original parenthesized expression for each one of those big N many data points. That's an important distinction to draw. So then after we do that for each of the in-sample points, expressed as the design matrix times the W matrix, take that result and subtract off the Y vector. Now we need to compute this square, all right, the squared part of the error loss. So we do that by taking the square of the norm, right, which is exactly that. So the norm is just you take any vector and you take the dot product of that vector with itself, and then you take the square root, right? That's what the norm is. So the norm squared is exactly what this squared error loss is in matrix vector notation. And then we have this leading 1 over n. We multiply by that scalar to represent the averaging that we're doing to calculate this in-sample error. Does that make sense? Okay. So in the in-sample error original expression, the role of that summation is to just accumulate all of the partial results of the sum of all those errors. So we compute the average, but we can do that in one fell swoop with that linear system, i.e. that big X design matrix. Okay? Questions? All right. So let's continue on. So now we have an expression for in-sample error, 1 over n, the norm squared. And that's exactly the same expression as En of h, where h is defined by that particular instantiation of a weight vector. But we have now an equivalent expression in matrix vector notation. So you could easily program something like this in MATLAB. You load in your data from CSV, you construct your design matrix, you do that multiplication, that subtraction, do the norm squared, divide by n, and there's in-sample error, right? And so the reason for doing it in this format is because you can compute this very efficiently. All right, so we have this expression, and now, of course, we want to minimize in-sample error. We want to select the hypothesis, or more correctly mathematically, or more specifically mathematically, the weight vector W such that we minimize this in-sample error. Now, the good news is for this expression, it's in closed form and it's smooth, and therefore we can take the derivative. It's differentiable. So how we're going to minimize this expression, and this isn't the only way you can do it, but because it's in closed form and it has nice, desirable, smooth properties, it's a lot easier to solve for W directly. And so you might be asking yourself, well, gosh, is that really searching for a hypothesis? Yes, it is. You're searching for the best hypothesis mathematically. It's just that this form of in-sample error, this coincidence measure between your ground truth target function and your current working hypothesis, this one lends itself to solving it mathematically. Now, could you do it in a different fashion instead of solving for it mathematically? Absolutely. You could choose a W, and then you search for a W that's nearby, and then you search for one that's nearby, and you keep iterating. And in fact, there's something called stochastic gradient that we'll talk about that does exactly that. But hey, if you have the tools of mathematics available to you, why not use it, right? Make life easy for yourself. So we're going to minimize this expression, 1 upon n, the norm squared of our design matrix x times w minus vector y. Okay. So we're going to take the gradient of this expression, and we're going to take advantage of chain rule in differentiation. So here we have an expression that's squared, and you can imagine almost doing u substitution. So we're saying u squared. So if you were to do chain rule, right, well, you do that u substitution, and then you need the Jacobian. So you say, okay, well, if I take the derivative of something with respect to w, and that something is like u squared, I get a 2, okay? And then I have 2 times what's inside that parenthesized or that expression, right? 2 times u, and then I have to take du with respect to that particular parameter w, right? And so if I do that, okay, well, I get the derivative of some quantity squared. Well, I have that 2, so there's my 2 upon n. 1 over n has not changed. And then I have my copy of this expression, xw minus y. Big X is my design matrix, W is my weight vector, and Y is my vector of real values corresponding to the outputs of the ground truth target function. So now, for the chain rule part, I take the derivative of this expression that's inside the L2 norm, my U in the U substitution, and I take the derivative of that with respect to W. Now, of course, the Y term does not involve W, so for all intents and purposes, it looks like a constant, so it goes to 0 if I take a ddw of this expression, and I have w raised to the 1 power, right? So I'm left with x if I do a ddw of that expression. So I get this other term here, x transpose. And if you think about, and I forgot this part, what it means to take the L2 norm, when you take the L2 norm, it's like taking the dot product of some quantity with respect to itself, right? And so if you're going to take the dot product of something with respect to itself, it's like saying, if I have x, it's like saying x transpose times x, right? That's what it means to square something in vector matrix notation if you're going to take the dot product of something with itself. And so you can imagine if you have a dot product for this term, and just think of this as a vector, because if you say the xw, that results in a 1 by d plus 1 vector. I'm sorry, in a d plus 1 by 1 vector. And so you're now subtracting a d plus 1 by 1 vector, a column vector from a column vector, right? So the rank portion of this design matrix that involves big N, that goes away, right? And you can even play this out, and I'll show you exactly that it does turn out the right way. So nonetheless, here we have two copies. We have this expression transpose times that expression, right? We took the derivative of it, something akin to doing U substitution, and we get that 2 coming out here times a copy, and then we have the derivative of this expression, the transpose version, with respect to W, right? And so if we do that, we get an X transpose here, and then we have another copy of that XW minus Y, and we set that equal to 0 and solve for W. Does that make sense? Any questions about this? No? You sure? Okay. All right. So if this is our expression, now we can clean that up a little bit, right? And so one thing I can do, we have a bunch of terms here times a parenthesized expression, and we set that to 0. And this expression represents the gradient of in-sample error in vector matrix notation set to 0 because we want to solve for W. So let's take this X transpose, and we're going to distribute that multiplication, this left multiply, into this parenthesized expression. And if we do that, what we get is the following. So we start out with 2 upon n, x transpose x w minus y is equal to 0. Okay, so we distribute this left multiplication of our x transpose, big X, and we get x transpose x minus x transpose y. Now, of course, when you're doing matrix multiplication, you really have to track and draw the distinction as to whether or not something's a left multiply or right multiply, because the rank of these matrices matters when you're doing multiplication. So you really have to pay attention and make the distinction of saying I left multiply or right multiply. This is a left multiplication. So we're just distributing that multiplication over the terms in this parenthesized expression, xw minus y. So we have that equals 0, and we write 2 upon n because that leading scalar, that hasn't gone anywhere. And it's the same expression. I mean, you could get back to this by factoring out that common left multiply by X transpose. That make sense? Okay, so now what we're going to do is we notice, okay, well, I have a 0 on the right-hand side of equality, and I distributed that left multiply by big X transpose, that linear system. I distributed that inside the parenthesized expression. So I'm going to multiply both sides of equality by n, right? So if I do that, on left-hand side, I get leading to scalar x left multiply x transpose x, x transpose left multiply y is equal to 0 because n times 0 times anything is still 0, right? Question? Oh, did I? Oh, my mistake. Whew, thank you for W. W did not go away. So focusing so much on the distribution that I wasn't paying attention. Thank you very much. Yes. So let me correct that. So we distribute this left multiply by X transpose, and we get X transpose XW minus X transpose Y, right? And so we get that expression. We multiply both sides of equality by n. N times 0 is still 0, always has been, always will be. And so now we're left with this expression. So then, again, we want to isolate the W because we want to solve for that. We divide both sides of equality by 2, right? And we get X transpose X W minus X transpose Y is equal to 0 because 1 over 2 times 0 is 0, right? So we do that now, and now we're going to bring this term to the other side of the equality, right? And so we're going to add now X transpose Y to both sides of this equality. So if we do that, of course, this term cancels out, and we end up with X transpose XW is equal to X transpose Y, right? Because 0 plus X transpose Y or 0 plus anything is additive identity, and we have X transpose Y on the right-hand side of equality. So now we're left with this expression, and we take that expression, and now we make an observation. We have this X transpose X. Now again, X is a design matrix, and we said the rank of the design matrix, big X, well, it was a column matrix, and it had n many rows, where each row was one of the big N many data points, and it had D plus 1 columns, right? Because you had a D plus 1 rank X vector. So we had X1 transpose, we had Xn transpose, as the rows of this design matrix, right? So anytime you write X transpose X, it doesn't matter what the rank is of this matrix, right? It's always a square matrix. And that's an important thing to think about. So if we consider this design matrix, we have D plus 1 dimensions, and we have n data points. So this matrix is going to be very, very tall and narrow, right? Because it's usually the case that you have a lot more data points than you do dimensionality. Now, a problem that might have 100 dimensions, that's a big representation, right? Even 1,000 dimensions, that's a lot of dimensions. But it's very typical to have thousands, hundreds of thousands of data points. So this X matrix tends to be very tall because n is pretty big, and much more narrow because you generally have relatively smaller number of feature vectors. Okay, so a rectangular matrix is not invertible, right? Because if you actually do out the math, the inverse is 1 over the determinant times the matrix of cofactors, and the determinant of a non-square matrix can be 0, and the thing just blows up and it doesn't work. So but if you have your X transpose X, well, what does it mean to transpose? It means you reverse the rows and the columns. So if X is n by d plus 1, that means X transpose is d plus 1 by n, by definition, because now your X transpose is going to look like the following. That means you're going to have X1 as your first vector. It's going to be a so-called column matrix. You can have x2 as your second, dot, 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 x big N as your last one, right? And this is a column matrix. A column matrix has each vector as its columns, whereas a row matrix, each vector is one of its rows. So again, okay, well, each one of these is d plus 1 dimensions, right? Each vector. So that's d plus 1 rows. And there are n many of them, so that's n columns. And therefore, the rank is d plus 1 by n. Okay? So if we were to multiply X transpose by X, well, we're multiplying a d plus 1 by n with an n by d plus 1. And wait a minute, all of a sudden, our resulting system is going to be d plus 1 by d plus 1. Okay? All right. So this all works out. And this step, we make the observation in this step that this X transpose X is a square matrix. Anytime you take a matrix transpose, you multiply it by itself, it's always square because of the way transpose works. Okay? So because it's square, we know it's invertible. A matrix is invertible. A square matrix is always invertible. Wonderful. So if it is invertible, we can left multiply by the inverse, and in doing so, we can get the left-hand side of this expression, this X transpose X will go to identity, isolating this W. Okay? So we're going to do that. So you can imagine I left multiply left multiply X transpose X inverse with this X transpose X. And if I left multiply on the left-hand side of equality, I'm also going to left multiply on the right-hand side of equality. Now remember, I had this X transpose Y on the other side of inequality. So I'm going to left multiply X transpose X inverse times X transpose Y, right? Oops, I forgot the W here. I keep forgetting that W. All right, so this X transpose X inverse times X transpose X, this is going to go to identity, right? So I'm going to end up with identity times W is equal to X transpose X quantity inverse X transpose Y, right? So identity times anything is the thing itself, and we end up with W, a definition for W. So we get W is equal to this X transpose X quantity inverse times X transpose Y. Does that make sense? Okay, now this is something you can do in MATLAB, but there's a function in MATLAB that will do it for you, and this thing has a name. It's called the pseudo-inverse. Now, you might be wondering, well, why is it called the pseudo-inverse of x? Why is this x transpose x quantity inverse times x transpose the pseudo-inverse? Now, if you think about what an inverse is, right? An inverse, imagine you have a linear system, and you start out with this linear system, um, X, and you have a bunch of elementary row operations that you apply in some sequence. And if you multiply those elementary row operations together, you get some other system, right? Now, imagine if you could apply these operations to X such that when you multiply elementary row operation 1 up through elementary row operation k, if you multiply that by x, you end up with identity, right? Um, this system, the product of all these operations, that's your inverse, right? Inverse is that thing that you multiply, and when you multiply by that inverse, it gives you identity, right? Now, in order to be inverse, it has to be commutative, right? So that means you should be able to left multiply, and and you can also right multiply, right? So let's define something called the inverse, right? Let's call the inverse let's give it a name, B, right? Let's say B is the inverse of X. Now, if B is the inverse of X, that means Bx is equal to identity. Likewise, Xb is also equal to identity, right? Now, it's called pseudo-inverse because this inverse only works with left multiply. It doesn't work with right multiply, right? That's why the pseudo part comes from. But you can actually demonstrate the pseudo-inverse part. If we were to take this expression and we left multiply it on x, what do we get? So if we say x transpose x inverse times x transpose, right? If we take this expression and we left multiply it by x, what happens? Well, oh, wait a minute. I have x transpose x inverse, and I have x transpose x. I multiply these two together, and guess what? I get identity. So it behaves like the inverse, but it doesn't fully behave like the inverse, hence the name pseudo-inverse. Now in MATLAB, there's a function, I think it's called pseudo-inv or something like that. But if you Google search it, you'll find the API call in MATLAB for calculating the pseudo-inverse, but there's nothing precluding you from actually doing it yourself the long way. Okay? All right. Any questions about this? So this is just to say, if you want to find the final best hypothesis, or we called it G, but that setting of W that minimizes in-sample error for this regression problem using squared error loss, that can be accomplished using this pseudo-inverse of the design matrix X. Does that make sense? Any questions about this? No? All right. Okay, let's see the time. It's 5:08. So let's take a look at how these dimensions line up. And our X transpose is going to be D plus 1 by N. So D plus 1 rows by N columns. And we're going to multiply that X transpose left multiply with X. And X is N by D plus 1. So it's going to be a square matrix. That's D plus 1 by D plus 1. Okay, so now we take that D plus 1 by D plus 1, and we take the inverse of that. Well, the inverse of a square matrix, it still has the same rank preserved. So it's going to be a D plus 1 by D plus 1 still, right? And then we take that D plus 1 by D plus 1 as a result of the inverse, and we're going to multiply it by X transpose. Now, multiplying by X transpose is D plus 1 by N, right? So the result is we're going to get a D plus 1 by N as a resulting linear system. Now, of course, we multiply that D plus 1 by N, we multiply that by our y, right? Now y is d plus 1 by 1, right? So we have that d plus 1 by 1, right? We're going to take this d plus 1 by n, and we're going to multiply that by this. No, y is n by 1 rather. Y is n by 1. I'm confusing myself. Y is n by 1. So we take this pseudo inverse, which is d plus 1 by n. If we multiply it by y, we're multiplying it by an n by 1, and that leaves us with a d plus 1 by n vector, which is exactly what we want, which is what w is. Does that make sense? Okay. Any questions about this? So what looked like it was really ugly and oh, how's that going to work? We had n. N is a scary thing because you can imagine if n is 100,000, if n is a million, right? And now we've reduced it down to exactly the rank of the weight vector w. Okay. So what is the algorithm for regression? You have your input data set, your label instance pairs, your in-sample points given to you, right, that you don't have control over. You take your X vectors and you put them into a design matrix, big X, row major, right? So X is going to be a row matrix. You construct from the target values, you construct your target vector out of all of the Y values associated with each of your in-sample points. You then compute the pseudo inverse of this X matrix, and then you solve the following solution for W, and you use that W as the value of the final best hypothesis. Okay? All right. Any questions? So it's pretty simple, right? Um, and it works quite well, and it'll give you that final best hypothesis W, and you can certainly do all of this in polynomial time. Okay? All right. So linear regression, it outputs real valued functions. Each one of these y values assigned by the ground truth target function is drawn from the set of real numbers. Okay, well, if you have a binary function from classification, we said at the outset that it can be a +1, -1 a y value representing the positive examples or the negative examples. Now, the number +1 and -1 represented one of two different decisions, one class or the other, but those numbers, +1 and -1, are certainly real numbers, right? Okay, well, you can absolutely use regression to try, and I stress the word try to solve a classification problem. In doing so, what you're doing is you're literally using pseudo inverse to solve for W such that it tries as much as possible to figure out what is the right W or hypothesis that solves for the assignment of +1s and -1s to each one of your inputs. So you could literally take a classification problem and solve it as a regression problem and use it as your solution. That makes sense? Will it be a good classifier? Absolutely not. It won't be the best classifier you can choose, but the beauty about this is that it's really trivial to solve the pseudo inverse instead of searching 10,000 rounds for PLA, right? So you could absolutely use regression to solve a classification problem. And then once you do that, right, you can use the sign W transpose X through a regression model to see if you agree, right? So once you get your regression W, right, you get this W solving through pseudo inverse. You take that W and now you compute sign W transpose X as your classifier, right? So you could absolutely train a classifier, find the final best hypothesis using regression. And you can do that quite easily in polynomial time through pseudo inverse. You could also use this regression to find for you very efficiently what is a good initial value of W for your PLA algorithm. Now, from the assignment, you saw that, gosh, well, I choose some value of W. And the initial value of W you choose can dramatically impact how good your PLA solution is, right? And so one of the hybrids that you can do or run is to start out in polynomial time, use pseudo inverse to find the initial value of W, set that W, and then run PLA using that W as a starting point, right? Regression is an absolute horrible classifier. It's not the best, but it tries as much as it can to agree with these +1, -1s as if they were real values, but they're really not real values. They're classifiers. Because the problem with that is that you could sign W transpose X, that could be -10, and regression would still try to make it a -1 if you solved it. And so with sine W transpose X, it makes no distinction between something that's a really obvious example of one class of the next, because regression will try to squeeze all of that into a plus one, minus one, and it's going to make a lot of mistakes. But it is a very good starting point. So, um, they had done some of this for the same 5 versus 1 binary classification problem of the two different types of digits, the 5-digit or the 1-digit. And this is the solution found using regression, right? So they took all the plus 1 examples, all the minus 1 examples, they solved it using pseudo-inverse, and this is the result they got. That's not bad for something that's so fast to compute in polynomial time using pseudo-inverse. So then after that, you take this as the starting point to initialize your PLA, your initial W, and then you just run your PLA update from there. Does that make sense? All right, so here it is. We had this PLA, it was very simple, and it introduced this issue of early stopping and also how you initialize this weight vector when you do your search. And now with this regression, we can combine the two and use regression to bootstrap or start your PLA search and get a very good result after a relatively small number of PLA updates. Does that make sense? All right. Any questions? No? All right. So let's take a look at this other related idea of nonlinear transformation. We said at the outset that PLA assumes that your data has this property called linearly separable. That means that you can take a linear model and you can use that to partition your data points such that the labeling from the working hypothesis agrees with the ground truth target function. And so in this example, this is a fictitious data set. And let's assume we have two features, the native features. We have the projection along the horizontal axis, and we have the projection along the vertical axis. And you can assume that the axes go through the middle of this rectangle or square, such that origin is right in the center, right? So if we look at it in this example, we have two different types of data points. We have one category, which are the red points, right? That might be the -1 class label. And we have the blue circles, which are here, and those might be the +1 class label points. Now, you'll notice here, these are arranged such that the red points tend to be more out away from the center, right? And the blue points tend to be closer into the center. And so that's not linearly separable. You can't find a line, a linear model, that will separate or agree with the class labelings. You could draw a line here, but it's going to get these red points wrong. You could draw a line here. Nope, still going to get them wrong. If you draw a line here, well, then it's going to get some of them wrong, right? This is not linearly separable. Now, if it's not linearly separable, could you run PLA? Absolutely you could. But it's going to make quite a few errors because you cannot separate the red points from the blue points using a linear model. It just can't be done. Now, certainly if you had something that was like a parabola, right, something that's a little bit more complex than a line, you could choose a parabola, something that's really, really eccentric, that curves a lot, and you could absolutely separate out the blue points here from the red points. But we don't have a parabola. We only have a straight line. A straight line is interesting because, as you found with the first homework there, the lab, it's very easy to update. W gets W plus YI XI, right? That's very simple, and you only run it for some fixed number of iterations. And we just saw with regression that you can bootstrap it appropriately, so you don't need that many iterations because you know a better way to initialize this W using pseudo-inverse. So if you could draw a hypothesis, something like a parabola or an ellipse, right, or something like that, you can actually get a very good separation that exactly matches the assignment of class labels, i.e. the red points from the blue points, right? So what can you do? Well, what you can do is you can perform a transformation on your data, change the values through some function, and when you do that, that rearranges the geometry. It changes the geometry of the data points. So this geometry of the original data, before you've made any modifications, everything is arranged radially, right? So as you get closer to origin, you get the blue points, but as your distance radially away from origin gets bigger, past a certain point, it starts to get more and more red, right? So with this transformation called the phi function, and we'll talk more about that probably in the next model. You can get this nonlinear behavior out of the same simple PLA linear model. And so the world is not always linear, right? That linearly separable is a simplifying assumption. Things like credit line. So the credit line that you can be assigned by a lending institution, it's related to the number of years that you've been in a house. But once you reach 5 years, it doesn't matter if you're there 6 years or 7 years or 10 years. It's just when you're there at least 5 years, things sort of aren't very different past a certain point. So you can think about it that the amount of credit you're extended increases, 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 and then you hit 5 years and it doesn't really do much after that. So it's not necessarily linear. So for example, less than 1 year, it might be really bad. Between 1 year and 5 years, it grows linearly. And then once you're over 5 years in residence, the amount of credit doesn't really change very much, right? 5 years is considered relatively stable. Okay, so regression had this value. We were coming up with a real value, and that real value represented a weighted sum. And that weighted sum we wrote in, when we talked about pseudo-inverse, we wrote the version of this sum in vector matrix notation. Now, of course, I'm leaving out the w, the minus w for the loss function, but the actual regression value, real value, you're trying to approximate what it is through weighted sum by choosing your w's appropriately. For classification, we talked about this +1, -1 uh, output from our hypothesis. And in each case, you can think of the inputs, our data values, our features, as being constants. And as such, when we talk about linear model, it's linear with respect to the weights, right? So those are the things that you're going to change, and those are the things that's linear with respect to. So you can think of you're solving for the W's, but the X's are like saying A, B, C, D. They're like constants because the X's are given to you, and you can't control the X's, but you can control the W's. And so the free variable that you have in your learning algorithm, you have the control over defining or finding some value for it is the W's. This is linear in W. Does that make sense? All right. So let's continue on and let's take a look. Because these X's are just another constant, it doesn't really matter what their values are. What matters is that the preservation, there's some relative relationship between them that's preserved, right? So let's introduce this idea of a so-called phi function. And this phi function is going to transform the data values from its original representation to some other representation. So in this particular case, we start with our original data set, and the data points are not linearly separable, the blue points from the red points. And so if we apply the following, well, these features, we have the x1 feature, and we have the x2 feature, and this pair, each one represents a particular vector, right? So this is a two vector. This is a two-dimensional feature space representation that is not linearly separable. So now, if we transform that, our phi function says, okay, well, I'm going to change the x1, the first feature, to be the square of the value of the first feature, right, from the original representation. And then I'm going to change the second feature to be the square of the second feature in the original representation. So one for one, this is the new value of that feature. And then here, x2 squared, that's the new value of the x2 feature. So for every single point, we have a corresponding, every single point x1, x2, we have a corresponding x1 squared, x2 squared. Does that make sense? And so what happens here? Well, given the value of x1 and x2, if x1 gets bigger, you go from blue to red. If x2 gets bigger, you go from blue to red, right? So what that does is that, well, if the blue points are closer to the center, that means that when you compute this x1 squared, x2 squared, that means the value of those points are going to be closer to origin. Now, in this transformed version, origin is here in the lower left corner. So we're changing the geometry. This is basically a polar transformation, such that points that are closer to the center have smaller values for each of those features, right? So you'll notice the blue points tend to be closer to the origin. In this case, is in the lower left corner in the transformed version of the space. And then points that are closer to the extremes, closer to the boundaries, they're further away from the center in the original representation. Now they're more to the right and up to the right, right? And so with this transformed version, all we've changed is the value of the features. And remember, the features are constant, so the linear model only cares if it's linear with respect to W. We've changed the geometry, right? This geometry so-called linearizes your data, right? So now with this transformation, and you can certainly do this in polynomial time, you can do this in big O of 1, right? You go through your data, pick the first feature, square it, pick the second feature, square it, and you can just do that in big O of n time, going through your excuse me, going through your n many data points. So certainly sub-polynomial time, right, depending on the constants, you can now produce this new geometry for that existing data. And it just so happens now this version is linearly separable. You can absolutely run PLA, and because it's linearly separable, eventually you're going to find the best hypothesis that separates the red points from the blue points. So here we have an example. You think of this linear model running PLA is very weak. It can't do very much, but just by making a few simple transformations or a few minor modifications, you can get some pretty powerful behavior out of it. We started out with plain vanilla PLA, and then we introduced this thing called the pocket version of PLA. You introduce one array that stores the best working hypothesis. When you add this change to the basic PLA, now all of a sudden it had this anytime quality to it where it didn't get worse. It always stays the same or gets better, right? So you didn't have this problem of early stopping. PLA was a linear model, and the data set, it could find you the best final hypothesis G if the data were linearly separable. And now we introduce this idea of a transformation, our phi function. And if you choose this phi function the right way, now you can find the best hypothesis using something as simple as PLA on the transformed version of the data set. Does that make sense? And so here it is. We started with this very, very simple, very basic PLA. And when you see it, you're like, is that it? It can't do much. Yeah, you're right. It can't do much. But by making certain changes, in this case to the geometry of the input representation, now this weak PLA can effectively draw what are called nonlinear decision boundaries, even though PLA can only do linear learning. Now, the beauty of this is that you pay this cost, the big O of n time, to do this particular phi function on your original data. But then after that, for learning, the cost you pay is just the number of iterations that you would for PLA, right? So it's almost like you get the ability to draw linear decision boundaries for free because the only cost you pay algorithmically is big O of n plus polynomial time for running PLA, which is kind of beautiful if you think about it. Does that make sense? All right. Any questions about this? Now, what we'll later learn, we could absolutely start with the original input representation with this polar geometry representing the arrangement between the blue points and the red points. And you say, okay, well, what's the equation for a circle? Well, I have an A and a B kind of squishing the circle in one direction or the other, and I have an x1 squared, and I have an x2 squared. Now, that's a lot more parameters than mx plus b for the straight line, right? Now, the consequence is you could absolutely have a more complex hypothesis, a nonlinear hypothesis that has more parameters, and you could absolutely learn from that. But how we pay for that is either needing more data, right, or relax our error tolerance because you can't get around the size of the hypothesis set. And certainly, if you have a straight line or linear hyperplane, that hypothesis set is smaller than something that's nonlinear, right? And we get that problem with the union bound where you have M, the size of the hypothesis set, that confounds your ability to guarantee that in-sample error tracks well with out-of-sample error, right? So this transforming of the geometry can get you a lot of mileage because you're getting nonlinear behavior, but you're only paying the cost of training a linear classifier. Does that make sense? Okay. Any questions about this? Oops. 529. I just dropped my comb. It's made out of wood, so I hope I didn't break it. Anyway, so one of the pieces of research that I did with a graduate student who has since graduated, he was an applied math PhD student, Piyush Sharma, was something called range transformation. And so one of the things that we found from a practical problem it started with, and it turned into a theoretical problem and really nice body of work, is that when you perform this transformation, this phi function, you're applying it the same way everywhere in feature space, right? And for some problems, well, in particular for clustering, you might not want to apply it equally the same way, right? And so in this case, when you apply this squaring of the first feature and the second feature, this polar transformation is done broad brush if you're in this part of feature space or if you're in this part of feature space or that part. It doesn't matter. Everything is treated the same. Now, of course, you have to sit and look at the data and think about, gosh, well, how is the data arranged? It's a polar arrangement. So let me choose a phi function that measures some notion of your radial distance from the center. If you make a mistake about how your data's geometry is arranged, you're going to do damage to the very pattern that you're trying to learn out of sample, right? And so one of the problems with these phi functions, especially if you have novel data, things that aren't typical, right? Maybe somebody develops a new sensor and you want to learn how to do classification or clustering. It's kind of hard to think about, well, what is the right transformation if no one has really seen this type of data before for some novel instrumentation. So what we thought was really what you want is you want some ability to say, let me transform the geometry differently in some regions from in other regions. And one of the examples we have is clustering. You have two sets of points, and what you really want is that when you want the points that are in the same group to be tight, close with one another, and you want points that are in different groups to be further apart from one another. And so we thought, gosh, how are we going to do that? And it would take me probably 3 hours to explain what we did. But in just sort of high level, we said rather than transforming the feature space representation, when you're comparing the ground truth target function to your current working hypothesis, that's basically a distance measure. You're measuring the difference or the relationship between two things, between data points, right? And so why not, instead of changing the representation, change the measurement instrument that you use to compare things, right? And so we call that range transformation because every input function for distance has a domain and it has the range. And what you're doing is altering this function in a prescribed way driven by optimization such that you get desirable ranges from your distance measure. And then you take this modified distance measure, you use it in your classification and your clustering to produce better performance for your classification and clustering. And so we did some theoretical work and we proved something called dilation ratio. I have the papers on my website, and then we wrote a journal article and tried it on a bunch of different application domains. And the wonderful part was the theory worked. We validated the theory from our proofs in a bunch of empirical measurements. And so the practical use does match exactly the theory, and we're very excited about that. And so this is just one example of a little bit more theoretical types of work, but it's based on some of the same ideas that we're talking about just in this third week of the semester. Question? Mm, okay. One application where we started was the classification of amino acid spectra. We collaborated with the optics group here at DSU on something called laser-induced breakdown spectroscopy. And so in that LIBS, or laser-induced breakdown spectroscopy, you measure the chemical composition of a compound without touching it. You focus a laser and then you pulse that laser, and that compound absorbs that laser energy and it starts to burn. And as it burns, of course, it's absorbing energy when you pulse with the laser, but as it releases energy, you take an accounting of all the different component frequencies of light, of the different colors, and those are indicative of certain chemical compositions. And so we had 6 amino acids. And if you think about amino acids, and I'm by no means a chemist or biochemist, I don't desire to be either. Um, what makes one compound different from another is one hydrogen bond or one extra carbon bond. It's very small, subtle differences. And so what we notice is that when we're trying to compute or make comparisons between amino acids based on their Lib spectra, that measurements for treating them as distributions and measuring the differences between those distributions, they weren't very effective because those differences were absolutely tiny. And so we thought about how can we improve this? And that's what led to this particular development. And so we created a new statistical measure called Shishini-Jensen-Shannon divergence. And we took Jensen-Shannon divergence and we reformulated it using the Shishini mean. So instead of using arithmetic means, we use harmonic mean and geometric mean. And it's not just limited to those two. And we found out that, oh my gosh, it works much better than regular Jensen-Shannon divergence. And so this whole work represented in this journal article, which was also the subject of Piyush's PhD thesis, was that exploration about why is it working so much better, right? And that's what this led to. And so that's one application. We used it in the computer vision, the image domain, in doing classification, and we got phenomenal results with that. And then there was another application that had a master's student, Michael Green, do using a wide area sensing platform, Gigapixel, to do scoring of regions of interest. And so the idea was to try to find things that were subtly or slightly different over a wide area. And so we did that. It's basically a camera, a type of fancy camera, and we were able to get some very good performance out of that. So we did it for live camera, computer vision. We did it for static images. We did it for protein amino acid spectra. And then we also generated synthetic data using multivariate Gaussian. And so we created the data. And the reason why we created our own data that was synthetic, because you could control how interspersed those categories were, right? And that's when we validated that the theory does hold true when you do it in practical measurements. So we did 4 different things: wide area sensing, static images, video images for directing a camera to actively seek out things in the environment that were only slightly different, as well as amino acid spectra, as well as the synthetic multivariate Gaussian data. Okay? All right. There was a practical issue with the wide area sensing because you're trafficking in a lot of data. It was really, really slow, right? So we could only make 2, maybe 3 comparisons a second. And if you're dealing with cameras live, you really want something like 10 to 20 a second. And so um, it would be nice to have some custom circuits to speed that up, or maybe do it on GPU or something. But nonetheless, we demonstrated what we were set out to demonstrate, and that says you don't always have to do a bulk transformation on the geometry. You can be more selective, and one way to be more selective is, instead of changing the representation, change the measurement device, essentially stretching the ruler in different ways that you use to measure differences with desirable properties. Okay? All right. Any questions? No? Make sense? Okay. So this is some work we did here. I think we got like, see now, two, three, 4 publications out of this work. Um, okay. So this is all just to say that what started as a very weak, very simple thing, most people, you see PLA and you're like, is that it? When are we going to do deep learning, right? That's what everyone says. When are we going to do the fancy stuff? But what seems like a very weak, very, not very useful in practical sense model, our linear model with PLA, it makes a very good building block for lots of sophisticated stuff. We've already seen now with the pocket, we can get anytime behavior out of simple PLA. With a nonlinear transformation, we can get nonlinear behavior, but we only pay the cost of simple PLA updates in that modified version of the space. And so you can also take this linear model and take more than one of them and use them in combination with something called soft boundaries, right? That's exactly what a neural network is. It's a set of linear models with these functions that are nonlinear functions computed from the weighted sum of those linear models, and you compose them with other weighted sums, and you get this sophisticated behavior in terms of describing hypotheses that do well with a large variety of problems. That's exactly what a neural network does, and that's exactly what deep learning is. And in deep learning, they have lots of clever and lots of elegant tricks and techniques in place to make the training of these large models much more simple and efficient, right? You can also find a boundary between the blue points and the red points from before in more interesting ways by adding, instead of just saying in-sample error, you add some other terms to that in-sample error that encourage certain types of solutions. And one way is using the gap or the margin between the red points and the blue points that are closest to the hypothesis. Now, support vector machines do that. Support vector machines are a type of nonlinear classifier right? And they're very efficient and do very well, and they actually derive from neural networks, right? But as a type of learning method or learner in and of itself, it's nothing more than a linear model with some additional constraints added on to the in-sample error that encourage certain types of solutions. So when we talk about regularization, we'll get to this idea of not only do you look for minimizing in-sample error, you can also say minimize in-sample error, but do it in a way that you're as far away from within the gap between these two different types of points. Okay? And so yet again, that is a linear model. By adding an additional penalty, you can get it to work in very sophisticated ways if you add a penalty or an extra term to the expression for in-sample error. Um, Also, going on these transformations that I talked about, we talked about this radial transform, the so-called phi function, and that's one type of transformation, but it's fairly naive. You can have much more sophisticated transformations. And if you choose these transformations in a way that they have certain specific desirable properties, you can get amazing nonlinear behavior without necessarily paying the cost of transforming it. So you can pretend it was transformed, pay the linear cost like a PLA, but not even have to physically do the transformation. And that special type of transformation is called a kernel, right? And that's what a kernel machine does. Now, some people think, oh, is a kernel support vector machine? No. Support vector machines use kernels, but you can use kernels with PCA, you can use kernels with all sort of applications. A kernel is just a specific type of transformation that changes the geometry of your original representation, right? But it has to have certain properties. And in this class, we'll talk about those properties, how you prove those properties, and what makes a kernel a kernel. Okay? All right, so kernel goes in the category of a special type of transformation, changing the geometry. And the beauty of a kernel, right, is that you don't even have to perform this transformation. If you satisfy certain properties, you get the effect of this transformation without paying the cost of this transformation. And it sounds weird for now, and I'll just leave it at that level until we get into regularization and kernels towards probably the 2/3 point in the semester. Okay? All right, any questions about this? So this is all to say what we first thought was a very simple, very weak type of model, the linear model with a simple PLA update. By making modifications to certain parts in the anatomy of the learner, we can use this simple, weak model as a phenomenal building block to do lots of powerful things. Okay? All right. Any questions about this? All right. So it is now 5:42. We have 3 more minutes. Let's end there, and I will see you two on Thursday. And we do have the assignment due on Thursday, right? So I look forward to them, and I will see you Thursday. Okay.